and we proved some theorem. Today we'll again continue the discussion on basis and dimension. Now the theorem that I'm going to discuss now is if theorem if W is a subspace of a finite dimensional vector space V, every linearly independent subset of W is finite and is part of a finite basis of W. Okay, so this theorem tells us that if W is a subspace of a finite dimensional vector space V, so our original vector space is V, and we're considering a subspace of this vector space, that is W. And so every linearly independent subset of W is finite and is part of a finite basis of W. Okay. So to prove this theorem, what we can do is we will consider a non-zero subset of W. Okay, and that subset has to be a linearly independent subset. So let S0 is a linearly independent subset of W. So this W is a subspace of the original vector space V, and I'm considering this S0 is a linearly independent subset of W. So what is the definition of linear independence here?
If we take the vectors of the set and we take the linear combination and set it to 0, then the coefficients are 0.
Yeah. So if S0 contains some non-zero vector, so S0 always contains some non-zero vector because this is linearly independent subset. So if I take the linear combination of the elements of S0, then and if that is set to be equal to 0, then all the, so just for an example, if S0 is the set of like U1 vector, U2 vector, UN vector, and if I take the linear combination of this set S0 of the vectors of S0, then that will be something like A1 U1 vector plus A2 U2 vector plus AN UN vector. And if I set this linear combination equal to 0 vector, then this equation implies that every A1 equals to A2 equals to AN equals to 0. So this is the definition of the linear combination, right? Okay. So, and now we are considering S0, and this S0 is a subset, is a linearly independent subset of the subspace W, right? And we already know from the statement of the theorem that V is what? V is finite dimensional. And so the number of elements in S0 always less than or equal to dimension of V. So since V is finite dimensional, then S0 contains no more than dimension V elements. So how can I extend this set S0 to a basis of the subspace W?
We find the vector in V, and then if we check that the span of S0 contains that vector or not, then we take the union of S0 with that new vector.
If that vector
is in V, but if we take a vector in V, and if we check that then the vector we are taking in V is containing the linear combination of S0 or not. Then if not, then we take the union of S0 with that vector.
Yeah.
And then we can have two bases.
Okay. So is that clear to you? What he is saying? Okay. So S0 contains some linearly independent vector, and we are trying to extend this S0 to a basis of this subspace W. So what we can do is, so what is the definition of the basis? So
This is a set.
yeah, then there
From where I can linearly take out everything in the vector space.
that means for basis, the linear there are two conditions for basis. The first one is the vectors in the basis set has to be linearly independent. This is the first condition, and the second condition is that set has to span the subspace, the vector space, right? So these two conditions has to satisfy, then that set we are going to call the basis. Okay. So and I am considering S0 to be a linearly independent subset of the subspace W. This is not still the basis of W, but we are going to extend this set S0 to a basis of W. So what we can do is we can choose a vector V belong to, let's just consider V1 belongs to the vector space V, and we have to check that if this vector V1,
First, should we go for V first or W? Because we took W as a subspace of V, right?
yeah,
So, like the induction way, we only address W, then we go for V.
actually we are trying to extend this set S0 to be a basis of W. Okay, so we'll choose a vector from the original vector space, and we are going to check if this vector you are considering is actually in the
In the subspace.
the set of linear combination of the the linear combination of the set S0. You need to check that. So what I'm trying to do is, so this set S0 contains some element that contains some vector. So, and let's consider span of S0. What is span of S0?
The subspace containing S0.
Yeah, there is another definition for the span. Actually, not a definition, we proved a theorem regarding the span.
All the subspace containing S0. Intersection of all the subspace containing.
That is the definition of span, but then we proved a theorem.
Linear combination of all the elements.
Yeah.
Linear combination of all that.
All the vectors of S0. Right? So, we are going to check if this vector v1 belongs to the span or not. So, let's consider if v1 belongs to, sorry, v1 belongs to span of S0 or v1 does not belong to span of S0.
S1.
Huh? Yes?
Is it S1?
S0
Oh, sorry.
of S0. So, if v1 belong to span of S0,
Or not belong.
yeah, so we are going to check if it is belong to,
Two cases.
yeah, two cases. So if it belongs to the span of S0,
Or
then
it doesn't belong.
we don't need to do anything with this vector v1. If this does not belong to span of S0, then we are going to make this new set S1 by S0 union this v1.
So when it doesn't belong, right?
Yeah. If okay. And this set is also linearly independent. Isn't it? Because we proved a lemma in the previous class. Is it clear that this vector v1, this set S1 is linearly independent? Yes?
But it doesn't belong to that.
No, I'm constructing this set S1 as the union of S0 and this vector v1.
Union of.
So,
Oh, then it will belong. Then S1 will have that.
yeah. So, do you want me to elaborate on this?
No, it's-
Okay. So, then this set is linearly independent, right? Now, again, we are going to check another vector v2 belongs to the original vector space v, and we again check if this v2 belongs to the span of S0 or not. If this v2 again is not belong to,
Same way.
yeah, S0, then we will construct that again another set S2, that is union of v1 vector union of v2 vector, right?
Or we could just say S1 union of V.
Yeah,
Just using the cascade.
yeah. And if we continue this process,
So Sn equal to Sn minus 1.
yeah,
Union of Vn.
yeah. And if we continue this way, then not more than dimension v steps, we will reach the set Sm, which is S0 union
Or Sn
of just sorry,
right, right, right.
v1 vector comma v2 vector vn, and this will be the basis of the subspace W, right? Then Sm will be the basis of W, will be basis of W. And
How about vector unions?
it depends.
Dimension of V or M, W.
I don't understand. Yeah.
So you just said that by continuing the steps, not can dimension of V or W.
Dimension of V.
V.
Yeah. So W can be equal to the original vector space, right? So then Sm will be a basis of W. And so this set Sm is the basis of W, right? And S0 is part of this set, right? So then from the theorem we started that subset of W is a finite and is part of a finite basis of W, right? We started with this at S0 and we saw that Sm equals to S0 union with all these vectors. So S0 is part of this set Sm, right? And thus the theorem is proved. Okay, so there are a bunch of corollaries from this theorem. The corollary one is if W is a proper subspace of a finite dimensional vector space V, then W is finite dimensional and dimension of dimension of V. So this is the first corollary. If W is a proper subspace, so this is important. Proper subspace of a finite dimensional vector space V, then W is finite dimensional and dimension of W is less than dimension of
You will prove that this theorem also in the last class.
we did.
Yeah, we did prove this. But I not like this statement, but we had another statement. But we
Okay,
did
so
prove this theorem.
In a different way.
Yeah, we proved it.
in different
Yeah.
This references.
Oh, okay.
I think we need to find the same literature.
Okay, I forgot that. I thought
We need to prove it. Did you prove?
We proved three ideas. Yeah.
okay.
Yeah.
Okay, so okay, did I prove this corollary as well? Or
You gave us key insights.
okay, so then I think I can skip the proof of this corollary, and there is another two corollary. Yeah, another corollary is
Corollary 2.
yeah,
In a finite dimensional
in a finite dimensional
there is no proof in the book.
vector space V, V every non-empty linearly independent set of vectors is part of a basis. So what this corollary is saying, in a finite dimensional vector space V, every non-empty linear independent set of vectors is part of a basis, and this is just a result we just proved, right? So as you can see,
We don't need any proof.
no, you don't, because
And if it is
this theorem, you see this theorem, yeah, W is a finite and is part of a basis of W. So you see,
I have a question.
yeah,
So if you are constructing basis,
Yeah.
not a construction. It is you are extending this finite set to a basis of the subspace.
yeah,
So if the finite set that you start with S0 is this set, if this set spans W, there is nothing to do.
right,
Now you are picking up an element from W that is not in the span of S0.
yeah,
You are supposed to take an element from W that is not in the span of S0. I don't think that it has to be a vector from the original vector space. And we keep continuing this process. And suppose then you get a new set by joining that new vector
yeah,
to S0. You call it S1. Then you need another vector that is not in span of S1. This new set.
yeah. Sorry, I
It is that you always have to refer to W.
because W is the subspace.
Is it given?
yeah, sorry. This should be W1 belongs to the vector space W, subspace W, right?
For corollary 1, that's it.
So we continuing until we saturate.
Yeah, we should start it.
So these A7 has to span W.
Yeah,
Then we stop.
yeah.
Right?
Right. Sorry for the misconception here. So for the second corollary, in a finite dimensional vector space V, every non-empty linearly independent set of vectors is part of a basis, and this is just the last line of this theorem. Basis of W. So if I just if I don't consider this W, then if I just consider the original vector space V, then the theorem, then the corollary just follows, right? Okay. Yeah. Is there any question? Do you have any question? So you see. Okay. Then there is another corollary that
So in original theorem, you replace W with V.
V,
Then you get this corollary.
yeah. corollary. Let A, B, and n cross n matrix over F. Suppose the row vectors of A form a linearly independent set of vectors in Fn, then A is invertible. So we need some results from our previous class, not just the class we just did. Probably I proved there is a theorem regarding like
Every square matrix is invertible. Sorry. Every square matrix which is a row reduced. Sorry, every square matrix having the row
no,
operators to
there's some
identity matrix, then the square matrix can be invertible.
so there is some equivalent statement.
Yeah, three.
If a square matrix is invertible, then there is this there is another statement that AX,
Multiplication will lead us to
yeah, it is just
identity matrix.
X if just let me if A, I'm considering A is a square matrix, so A is invertible, then sorry, then the equivalent statement is that Ax equal to 0.
You can remove the if from the
Sorry, right. A is invertible, then Ax equal to 0. Yeah. Then there is another statement.
No, the second statement A is equal to 0 has trivial
Oh,
solution.
sorry, has trivial solution. Trivial solution.
Has only the trivial solution.
Right. Only.
Which means that A is equal to 0 does not have a non-trivial solution.
Right. So
A can be reduced to the identity.
A is row equivalent to the identity matrix. So we need these results to prove this corollary. Okay. So a scratch of the proof can be like, okay, over F, suppose row vectors of A form linearly independent set of vectors, right? So A is a n cross n matrix, right? If A is a n cross n matrix, then I can consider the row vectors of this matrix as alpha 1, alpha 2, alpha 3, dot alpha n. These are the row vectors of this matrix A, right?
If they are the row vectors, why don't you write them as alpha 1, alpha 2, alpha 3, all the way down to alpha n as a whole?
Okay, so
That way it manifests that they are row vectors, right?
So A is just simply like A11, A12, A13 dot A1n, then A21, A22, A23, A2n, A n1, A n2,
or in my
n3, A n. So I'm considering this matrix. Then if I just take this row to be alpha 1 and the second row is alpha 2 and the nth row is alpha n, then all these alpha 1, alpha 2, alpha 3, alpha n will be row vectors, right? Okay.
reduced
And
color vector.
yeah, in the statement of the corollary, it says that let A be an n cross n matrix over the field F. Suppose the row vectors of A form a linearly independent set of vectors in Fn. Then A is invertible. So there are n row vectors here, right? Okay, so and we know that the standard basis of Fn is what? Yeah, Fn will contain. Yeah, I mean, in the standard basis of Fn, there are n linearly independent vector, right? Okay, so let us consider let u1, u2, un. This is the standard basis of Fn.
And linearly independent vectors.
Yeah. This is
Because A is a dimension vector.
yeah standard basis of Fn. So why n is the dimension of Fn?
Because there are the linearly independent set consists of n elements.
N elements.
Yeah, but why?
Yeah.
Why?
So it is n dimension, is finite dimensional, and the dimensions are.
No, we define the dimension as the linear number of linearly independent vector
There are
in the
number-
basis
in number of linearly independent, and
vector.
they span the whole vector space.
That is called the dimension.
So that is
Yeah.
called the dimension.
We define the dimension in terms of the number of linearly independent vector in the basis set.
It is.
Yeah, right. So this is the standard basis of Fn. So yeah, so what we can do is now we can write this we can write each of these u1 as a linear combination of the of these row vectors, right? So u1 will be like some
Why?
Or reverse. It should be reverse.
right.
Alpha 1 will be the linear combination.
The basis.
Right.
Okay, let me think about it first. So what I want is I want to replace this with this thing. Okay, so this will be something like alpha 1 is equals to x1 u1 vector plus alpha 2 sorry x2 u2 vector plus xn un vector, and this is just simply x I uy vector I equals to 1 to n. Okay, so what I want to do is matrix here. And this is not the way I want to do it. Right. So, is invertible x equal to 0 is only trivial solution.
So we see this in the book, they say that one of the row vectors, and then suppose that there is subspace of defense and the other one of the two. So they give linear combination of one of the two.
Yeah, because I think they are doing so because what are you thinking? Just go back to the statement. You know that A is an n times n matrix over F.
Yeah.
Suppose the row vectors of A form a linearly independent set of vectors in F to B. Right?
Right.
So each row vector that G denoted by alpha I, right? Each of these vectors, the set consisting of these vectors, alpha 1, alpha 2, alpha n, these are all linearly
Independent. Yeah.
And there are n vectors in this set.
Right.
And n is the dimension of F to B.
Right.
That has to be a basis.
Right.
So that is the logic. The logic is that F to the n is n dimensional. I think there was a result in one of the previous theorems that if the dimension, if you have, suppose a vector space has dimension n and you have n linearly independent vectors, that must be a basis.
Yeah.
So it has to span the vector space automatically because the number is the same as the dimension of the vector space.
Yeah. So
that actually works as a basis.
Yeah.
In that case, alpha and alpha 2 are the basis. We don't need U1, U2.
You can write U1, U2 as linear combination of those guys that Jim started.
So there is a result. So if two bases of a finite dimensional vector space, so there are equal number of elements in these two bases. We proved a theorem regarding this results. And okay, so
I think the result that we need here is that n is the dimension of F to B.
right.
And there are n linearly independent vectors in that set. So that has to be the basis of F to B. Right?
Right. So also I can write alpha 2 is equals to summation of I equals to 1.
Are we doing this or we are writing U1 vector as a linear combination of
Yeah.
the thing that you started with?
I think that is the result I need, right?
That's what we need.
So U1 vector is equals to x1 alpha 1 plus x2 alpha 2 xn alpha n. So this is simply summation of I equals to 1 to n alpha 1 just
xi
alpha I. But these I can write in terms of like they're in component vectors, so this is simply alpha I is a column like row vector, so this is something like I can expand it like in terms of the matrix element.
What you could do is that you could write u1 vector as x1I alpha I, and u2 vector is x. I mean, that without writing x, you could write it as some matrix.
Yeah,
The
that
entry
I
of the
want.
matrix. That way you capture the matrix entries.
So
So in general, you could write like ui vector is equal to sum ui vector is equal to sum over sum of from I equal to 1 to
yeah,
from not I or j from 1 to n, and then some a big A matrix ai j alpha j vector.
Yes, that makes sense.
Right? Now we are looking at this matrix.
It's much better.
right.
Is it what you want to do?
Actually, I need to construct a equation like alpha ij times the scalars, because alpha j is not a scalar. This is a nth component row vector. That's why there is a problem. Okay, so let me look it up. I did a proof on this.
The proof in the book is very unclear.
What is it?
Because if you look at this, clear.
Yeah, this is what I see in the book. Where these is the standard of the matrix B is EIG.
They suddenly rewrite the equation.
Okay, yeah, now I understand. So this aij, it is not the aij. It is yeah,
Oh, you write it with BIG.
yeah, right. So this should be bij. Then bij times alpha j. This is a linear combination for the for this ui, and we know ui, yeah, is a standard basis element for fn. Thus, for the matrix B with entries bij, we have
Yeah,
I didn't understand.
okay. So the idea is here this bij. I'm multiplying this bij with alpha j. So what I can do is I can construct an identity matrix using this ui, because this will be 1 0 0 0 0 then the second element with 0, 1, 0,
Why?
0,
Why?
because every ui can be written in terms of this equation, right? Now just consider this. So for the a cross a matrix, so when I'm considering this a matrix, this was this, right? But I can write that matrix in terms of the row vector alpha 1, alpha 2, alpha n. And now just consider, so if we consider the standard basis of fn, we know the standard basis of fn is what? 1, 0, 0, 0.
Oh, that's the standard basis.
Yeah, then the second one is 0, 1,
Oh, okay, sir.
0.
That's by definition.
Yeah. Now, if you stack all these standard bases in a matrix form, you will get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0. This will be the matrix you can construct from the standard basis. And this is equals to what? This is equals to j equals to 1 to n beta ij times alpha j.
We do some of our horizons as well. Because
Yeah, right. No. So it's not sum over I. So I have to take all this, like this should be, yeah. Okay, let me just write this. Okay, so j equals to 1 to n beta 1, I mean b1 j alpha j. Then the next entry will be j equals to 1 to n beta b2 j alpha j, and the final entry will be j equals to 1 to n bn j alpha j,
okay, so that makes sense.
right?
So these are row operations, right? So we have finite number of
Yeah.
row operations, and we are getting the identity matrix. That means it is row equivalent. They are row
Yeah.
equivalent. So the root rows.
It's just a result, right?
So their identity matrix, so the row equivalent and identity matrix. That means it is invertible, right?
I mean,
On the left side, this
if
is-
you use this this,
Yeah.
right?
Yeah.
is good. Oh, okay.
So this matrix is invertible. This bij, if I multiply bij with alpha j, this is what I can write the right hand side in terms of the matrix B with the matrix A, and I'm getting in the left hand side the identity matrix, right? So B is definitely what?
Row operation.
The inverse of
Inverted.
A,
Yeah.
right?
Of course, then it's inverted.
That means A is invertible.
Okay, so the first row there on the right hand side
Yeah.
is BA. What is this? BA1, right?
B1J, sir.
Yeah.
That should be A.
If I try to write it, is the first row of the matrix B times A.
Yeah.
Oh, okay. Right. Then it should be
You need to understand it clearly that these right hand side actually is the same as B times A.
Is that clear to you? Why?
A. Then we have to expand, yeah. Because
You have
alpha
to
J.
expand.
Yeah.
These are rows.
Yeah.
Alphas are rows of A.
Right.
So all these rows, this is a row. The second one is also a row.
So
That-
what I suggest that why don't you
Expand.
do that? Alpha these alpha, so in the beginning, Jim wrote these alphas as A1, 1,
Right.
B. So just write those expressions. Replace AJ with those.
Yeah. Okay.
So then they will be able to see that this is actually B times. It is
Right.
important to see that it's B times.
So I'm considering this matrix B with this A. Okay. So, but what is A? A is simply, so I'm considering this matrix B with A is simply what? Alpha 1, alpha 2, dot dot alpha n. And also, what is this B matrix? B matrix is A. As you can see, B is what? The every element in here is what? Running from 1 to 1n, right? So the first row will be what? B1 1, B1 2, B1 n, right? Then the second will be B21, B22, B2n, and this is Bn1, Bn2, Bnn. This is the B matrix, right? And I'm multiplying this B matrix with this alpha 1, alpha 2, alpha n, right? So, and that's why I can write this as this, and left hand side this is the identity matrix, and in the right hand side I started with this matrix A, and I'm multiplying this matrix A by this matrix B, and I'm getting this identity matrix. Then that means B is definitely the inverse of this matrix A, and so this matrix A is what? It is a invertible matrix.
So we did not prove that this is equal to A times B.
Yeah, for the right hand side I can do the same, right? I can multiply this by the right and I can get the same results, because alpha I is a row vector, so there are n element, and in the B there are also n columns, so I can multiply it by right hand side. So that's why the result follows. Okay, so okay, so there is another theorem here. Theorem: if W1 and W2 are finite dimensional, subspace of a vector space V, then the sum set W1 plus W2 is equals to W1 plus W2 such that W1 belongs to the subspace W1 and W2 belongs to the subset W2 vectors. Is finite dimensional and dimension of W1 plus dimension of W2 is equals to dimension of W1 intersection W2 plus dimension of W1 plus W2. So we are considering two subspace of this vector space. The first one is W1 and the second one is W2. And these are finite dimensional subspace of vector space V. So also this vector space V is also finite dimensional. Then the sum set W1 plus W2, we already defined what sum set is, right, in one of our previous lectures. The sum set W1 plus W2 is defined to be the first element comes from the subspace W1 and the second element comes from the subspace W2, and we are adding these two vectors. This is how this W1 plus W2 space defined. So this, yeah, yeah, we already proved that in previous. So this sum space W1 plus W2 is a finite dimensional, and the dimension W1 plus W2 is equals to dimension of W1 intersection W2 is plus dimension of W1 plus W2. So do you remember what was the definition of the, yeah?
Is that class a direct sum or in that?
So yeah, I'm going to ask you that question. So why this is not a direct sum, and when this will be a direct sum? Because
when we have intersection equal to 0, then we have a direct sum.
yeah, exactly. So when we if the sum is a direct sum, then this,
unique representation of 0 in every.
yeah. So if the sum is a direct sum, then dimension of W1 plus dimension of W2 will be what? Can you just conclude the that from this?
The sum of the dimensions, right?
Yeah, because if you so the dimension of zero vector, only the vector space consisting only the zero vector, this
So it's 0.
it's zero dimensional vector space. So then the result will be dimension of W1 plus dimension of W2 is equals to dimension of W1 plus W2. Okay. So let me sketch a proof of this theorem. Proof. So what will be the so this set, let's first consider W1 intersection W2. This will be a finite dimensional vector space, right? Okay. And why this is a finite dimensional vector space?
Because the intersection is smaller than intersection is contained in W1 and W2. So if W1 and W2 are finite, then intersection will be finite.
Is it understood why this is a finite dimensional? Because they say W1, the subspace W1 and W2, they are finite dimensional.
The finite dimension.
Yeah.
So the intersection will be also
Yeah. Finite. So then W1, W2 is also finite dimension.
finite dimension and finite basis the same thing.
Yeah, because we define dimension in terms of
Basis.
the number of elements in the basis set.
Basis set as a dimension.
Finite dimension. Okay. Suppose this set, this subspace W1 intersection W2 has the basis. Suppose W1 intersection W2 has a finite basis U1 vector, U2 vector, UL vector. So this set, this will be this is going to be part of the basis of W1 and W2, right?
Yeah.
Why is that?
Because linear span of these elements also contains in W1, right?
No, because from our previous theorem, the theorem that we proved in the beginning of this class, that if I take a linearly independent set in a vector space, then that set will be part of the basis of that vector space, right? So since this is a basis of the of this subspace, then that means, and this set is linearly independent, right?
So what is this UL?
Yeah, this is UL, this is the element.
Oh,
Okay, so this is a vector.
Since it is the basis, they are
They are
set is a linear.
linearly independent. So, and since it is linearly independent, then it is definitely part of the basis of W1 as well as W2, right? Yeah, so in the
kind of tautology. You said first you said this is a basis, then you said
No.
independent.
It
Then
is
it's a linear independent, then it's a basis. No.
no. This is that is not I'm saying. What I'm saying is I started the class with the theorem,
Right.
and that theorem was what? If you consider a finitely independent, a linearly independent subset of a vector space, then that will be the part of the basis of that vector space, right?
Every subspace of finite dimensional basis. Every linear independent subset of W is finite. Right? And it's part of the basis.
Part of the basis, right? So now I'm considering this subspace W1 intersection W2.
It's also a finite dimension.
Yeah, and this I'm considering this set U1, U2 dot UL to be a basis of this set W1 intersection W2, this vector space, right?
So this thing is a basis of W1 intersection.
Yeah. So since it is a basis, it is what? It is linearly independent.
First we say basis.
Yeah. So since it is a basis, so it definitely a linearly independent set. And since it is a linearly independent set, then this is part of the basis of the subspace W1 as well as the subspace W2.
Circular logic. So now you say since it is linear independent, so it is basis.
No.
Now,
That's not what he's saying. He's saying that according to the theorem, as long as you have a linearly independent subset, that is going to be part of a basis. It is not part of the basis. Because the basis does not make sense. There can be many bases of the same vector space. So the theorem assumes that it is going to be part of one of the bases of the vector space. So W1 intersected with W2 is a vector subspace, and hence it has a basis. So he wrote down a basis.
So
U1, U2, UL. It is a basis, and hence it is a linearly independent set. Now we invoke the theorem that he opened the class.
yeah, the hierarchy is I'm considering this set U1, U2 dot UL. I'm considering this set as a basis of this set, this subspace W1 intersection W2. Okay. So since it is a basis, then it definitely linearly.
So this is logic step 1.
Yeah.
Logic step 2. Since it is linear independent, so it is a basis.
No.
Basis. So the last branch of the answer.
Okay. So since this set is a linearly independent set, then this set is what? আই মিন এবং আমরা ইয়েটা থেকে কি দেখেছি আর কি, যে আমরা থিওরেমটা থেকে কি জানি, যে হলো লিনিয়ারলি ইন্ডিপেন্ডেন্ট সেট সবসময় কি করে, পার্ট অফ দ্য বেসিস, রাইট?
Not part of the
Sorry, part of a basis.
Forget about so use the languages properly. So it is going to be part of a basis. এই জিনিসটা যেটা আছে এটার সাথে আমি আরো ভেক্টর অ্যাডজয়েন্ট করে করে বড় ভেক্টর স্পেসটার একটা বেসিস তৈরি করতে পারবো। This is what we are saying. So these u1, u2, ul, you have to adjoin vectors to it, and then form a basis of w1. Similarly, a basis of w2, according to the theorem.
Yeah. So is that clear?
Theoretically, wording কি হবে? Vector বলছে যে if W is a subspace of a finite dimensional vector space,
Right.
V, which W is a subspace of a finite dimensional V, then every linearly independent subset of W is finite and is part of a finite basis of W.
Right. So let me explain. এখানে যে ব্যাপারটা হচ্ছে এখানে একটা বড় ভেক্টর স্পেস আছে, তার একটা সাবস্পেস দেওয়া আছে। এবার আমি W একটা লিনিয়ারলি ইন্ডিপেন্ডেন্ট সাবসেট নিয়েছি, সাবস্পেস। এখন থিওরেম বলছে যে এই সাবসেটটা যেটা নিলাম W, এটা W এর একটা বেসিসের পার্ট। ইন আদার ওয়ার্ডস এই সাবসেটটাকে আমি ওই W বেসিসে এক্সটেন্ড করতে পারবো। মানে এই যে সাবসেটটা আছে এটার মধ্যে আরো ভেক্টর ঢুকিয়ে 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 আমি W এর একটা বেসিস ফর্ম করতে পারবো।
Right.
This is what it is saying, right?
And and just just replace the V by W1 in the theorem, and for W you have to replace by W1 intersection W2.
Then you have this.
Right? Is it clear? So you have to replace, like in the theorem we started with this vector space, and there is a subspace of this vector space, that is W. So this is the vector space, and this is the subspace. Then we said that there is a set S0 which is a subset of this vector space W, and
The
this
subspace.
subset.
Subset.
Yeah, so this is the subspace. Yeah. So S0 is a set that is a subset of the vector subspace W. Okay. Now, and S0 is linearly independent. Then from the theorem we know that S0 is part of a basis of W. Okay. So this was our theorem. Now replace V by W1, and just for now consider W1, and W by W1 intersection W2,
So then it becomes subspace.
right? Then you will get that S0 is a
Subset of W1
part of the basis of W1 intersection W2, and hence it is also part of the basis of this
W1.
vector space, subspace W1, right? Is it clear now? Okay. So
No, S0 is
part of a basis.
not part. S0 is a linearly independent subset of W1 intersected with W1.
Yeah.
And from which you conclude that S0 is part of a basis of W.
Yeah,
S0 is a linearly independent subset of W1 intersected with W.
yeah,
What is S0? The basis that we chose for
Right.
W1 intersection.
yeah, yeah, right. So S0 is here just what I choose for U1 vector, U2 vector, dot dot, UL vector.
You will get. That is S0.
That is, I'm considering as S0. Okay,
Okay?
okay. Then I can extend this set U1, U2, UL to a basis of W1 as well as to a basis of W2. So,
Next time again, you also take V to be W
okay,
and a smaller set to be W1
Yeah.
intersected with W2 and you get the same thing.
right. So, I can extend this set U1, U2, UL to be a basis of W1 as well as to be a basis of W2. So, what I can write is U1 vector, U2 vector, UL vector, V1 vector, Vm vector. Let's consider this to be the basis, this to be a basis for W1 and U1 vector, U2 vector, UL vector, W1, Wn vector for,
You can consider writing basis.
yeah,
Yeah.
basis for W1 and W2. So I'm considering these two set.
M does not need to be equal to N
Yeah.
in general.
Yeah,
Okay?
right.
They can be very different.
Yeah, because I'm considering arbitrary two subspace W1 and W2. So the subspace W1 plus W2 is spanned by the vectors belonging to the following set. So the subspace is spanned, sorry, yeah, W1 plus W2 is spanned by the vector belonging to the following set. U1 vector, UL vector, V1 vector, Vm vector, sorry, W1 vector, W1 vector. Right?
So we construct this using the union rule, right?
Yeah. Belong
Just
to,
taking the union of those two bases.
yeah, because we know that so this set, the span of this set contains all the linear combinations of all these vectors, right? Okay. So now the claim is that the set above is linearly independent set. Is it linearly independent? So let's consider I equals to 1 to L alpha I ui vector plus j equals to 1 to m beta j vj vector plus k equals to 1 to n gamma k wk vector equals to 0 vector. Okay, so now I can write it minus k equals to 1 to n gamma k wk vector is equals to I equals to 1 to L alpha I ui vector plus j equals to 1 to m beta j vj vector. So according to this equation, this vector, this belongs to the set, belong to the subspace of which one?
And this will be W1,
W1, right?
W2.
W1,
Okay,
right? Because I considered the basis of W1 as this. So a linear combination of that basis vector will be the subspace W1, right? So the left hand side, the vector, this is actually what? This is a
this is a
element of W1, right? But this is also belong to, why is that?
because the WKs are the basis of W.
Because Wk is the these vectors Wk's are the elements of the basis of W2, right? Yeah. So that means this vector k equals to 1 to n gamma k wk vector is also belong to W2. Then this vector is actually belongs to the intersection. That means k equals to 1 to n gamma k wk vector belongs to W1 intersection W2. Okay, so what I can write is, so since this vector belongs to the set W1 intersection W2, that means we already know we choose a basis for W1 intersection W2, and that is U1 U2 dot dot U L, right? That was the base, that was the basis of the vector space W1 intersection W2. So I can write this as what? K equals to 1 to n gamma k wk vector is equals to, just consider I equals to 1 to L rho I ui vector, right? but we know that this set u1 vector, comma u2 vector, ul vector, comma w1 vector, wn vector, this set is linearly independent because it is a basis. So this is
The basis of W2 or W1?
this is w1, sir. Basis. Sorry, it is the basis of w2. W2.
That's rho I, ui.
Yeah, this is rho iui.
So each of these coefficients are 0.
Right. So since this is a basis, and in the right hand side all these ui, these are also a basis. So this set is linearly independent, and in the right hand side that set is also linearly independent. So what we can conclude is all these gamma 1, gamma 2, gamma n equals to u1 equals to u2,
Rho
sorry, ul equals to 0.
1. No. Why you?
Sorry, this should be rho. Rho 1, rho 2, rho n. This is equal to 0. And since this is equal to 0, so from this equation what I can write is the right hand side is also equal to 0, right? So I equals to 1 to L alpha I ui vector plus j equals to 1 to m beta j bj vector. Bj vector, this is equal to 0 vector. And we already know that ui, so u1, u2, ul, v1 dot dot vm, we choose this set to be the basis of w1, basis of w1. So since it is a basis, right? So since it is a basis, it is linearly independent. That means all these coefficients alpha I equals to beta j equals to 0. Is that understood? Why all these coefficients are 0?
Some definition of linear independence.
Yeah. So is it clear why all these coefficients are 0? So the right hand side is already 0 vector, because we showed that from this all the gammas are 0, right? So since all the gammas are 0, then the left hand side, this is what? This is 0 vector. So I wrote it here. right? Now, so in the left hand side, now I am considering the linear combination of the set u1, u2, ul, comma v1 dot dot vm, right? But I took this set u1, u2 dot dot ul, comma v1 dot dot vm, this to be a basis of w1. So since it is a basis of w1, it is definitely linearly independent. And if this set is linearly independent, so from the definition of the linear independence, we know that all the coefficients has to be equal to 0. So I am concluding alpha I equal to beta j is equals to 0.
Now, so the first part, why gamma became 0?
This one, this one,
Can you please go up?
in the previous one,
Yeah, the previous one.
gammas.
Because of the basis of the two? No.
On
Why
which
gamma
part?
one, gamma two? This equation.
Okay, so you are considering this one. Okay,
Why
so
became
okay, so as you can see that the linear combination of this is also belong to W2. Do you understand why this belongs to W2? Because
it is different than W1.
so just so what is the basis of W2? The basis of W2 is this one,
Yeah, we different than this.
right?
W1.
So if I take the linear combination of this part, then you will get the vector, and that vector belongs to the subspace W2, right? Because this is the basis. So this is just the linear combination of all these W's. So since I am taking the linear combinations of the basis elements, then this vector is in the vector space W2, right? Okay. So this belongs to the vector space W2. Now, also, what is this? Yeah. So, yeah. But from the left hand side equals to right hand side, now consider the right hand side. Right hand side is the linear combination of the basis of which vector space? Which subspace?
Right hand side.
Yeah, the right hand side, this side,
W1.
this is W1. So then this part is belong to the W1, right?
Right hand side W1.
Yeah.
Left hand side W2.
Yeah. So that means this vector, this one belongs to the subspace W1 intersection W2, because this vector, right? Okay. Then yeah. So
I don't know. You're not following the book, right? It's different way. Your group.
yeah,
Yeah, that's what.
there is some differences. Okay. So now, so since this vector belongs to the say W1 intersection W2, and we already choose a basis for this intersection subspace W1 intersection W2, right? And that is U1, U2 dot dot UL. So I can write any vector of W1 intersection W2 as a linear combination of this basis U1, U2, UL, right?
Whenever there is a basis, I can conclude these scalars, like gamma 1 or rho 1 or s.
No. So if you have a basis of a vector space, yeah, every vector in that vector space is a linear combination of this basis. So since this left hand side, so this vector belongs to this vector space W1 intersection W2, and we have a basis for W1 intersection W2, and that is this. Okay.
I'm fine with it. I'm just.
So no.
The 0 K. That's what I'm saying.
Okay. So just
So if you just shift that to left hand side to right hand side, then we have linear combinations of W's and U's equal to 0 vector, right?
no. Just
So we can say, since it is a basis of W2, so we can say that it is all the coefficients.
yeah. So just let me write another line here. So I can write this line by summation of k equals to 1 to n gamma k wk vector, and this is minus summation of I equals to 1 to L rho I ui vector, and this is equal to what? 0 vector, right?
That equation. Yeah.
So then you already know what. So yeah. No, actually I don't need to write it in terms.
You need to. So suppose you have that. Okay. Now you know that this guy is the basis of W2, right? U1 vector, U2 vector, UL vector, W1 vector, Wn. So it is a basis of W2, which means that it is a linearly independent set of W2. So now the left hand side, what Jim just wrote, gamma k wk vector minus that one. So the left hand side is a linear combination of this linearly independent set, right?
This one.
And you set it to 0 vector. So now from the definition of linear independence, it follows that all the scalars are 0.
Okay.
Is it clear? It follows from the definition of linear independence.
Yeah. So that's why all these coefficients gamma 1, gamma 2, rho 1, rho 2, rho L is equals to 0. Now, since this vector, I'm considering this one, so if all these coefficients gamma 1, gamma 2, gamma n equal to 0, then the left hand side is what? Left hand side of this equation, this is equal to 0 vector, right?
The rest follows here.
Yeah. So since this is equal to 0 vector, and in the left hand side again I am getting a linear combination, and that linear combination equal to 0 vector, and since
Again, you invoke the definition of linear independence.
okay. Okay. So the next part is coordinates. Okay.
The
Okay.
dimension thing that you explain, that how you
Oh, okay. So sorry. Yeah, I forgot. Finally, so dimension of W1 plus dimension of W2, this will be what? So we know what is the definition of dimension in terms of the basis, that the number of
Elements.
element in the basis set. So how many elements in W1? Sorry, in the basis of W1. In the basis of W1. Yeah. So that is L plus L plus N. Sorry, M, right. And how many elements in the basis of W2? L plus N. L plus N. So I can write it like this: L plus M plus L plus N. Right? So L is what? Dimension of W1 intersection W2, and this is plus equals to what is M plus L plus 1 in why?
Because
because of this. Okay, so yeah, right. So that means this is dimension of W1 plus W2. Okay, and then you can just conclude uh, the same theorem for the direct sum, and that will be
W1 intersection
yeah.
W2 equal to 0.
Yeah. So dimension of W1 plus dimension of W2 is equals to dimension of W1 plus W2, and W1 intersection W2 is only the zero vector.
So you write direct sum.
Yeah. Right. This is the direct sum. Okay. Okay. So can I continue for a few minutes? Okay. So let us consider the coordinates. So definition: if V is a finite dimensional vector space and ordered basis for V,
So you're defining ordered basis.
yeah, V is a, so far the basis we defined, that was not an ordered basis, so you can just exchange one vector by another in the position. You can change the position of that vector space because there is no order in a set. Right? In general, there is no order in a set. So now I'm defining the ordered basis. If V is a finite dimensional vector space, an ordered basis for V is a finite sequence of vectors which is linearly independent and spans V. So this is the definition of the ordered basis. So if V is a finite dimensional vector space, and ordered basis for V is a finite sequence of vectors which is linearly independent and spans V.
So you're replacing set with sequence.
Yeah.
So that order matters.
Right. So there is a direct relation from the when we consider the sequence as a map from the natural number to the sequence space, right? So since the natural number has a order, that's why
It will be an ordered set.
yeah, the sequence is the order set. Speak. Okay, so there is a remark. If a sequence U1, U2, UN is an ordered basis, ordered basis, then the set set u1, u2, un vector is a basis for V.
Okay, you can see that when he writes a sequence, u1 vector, u2 vector over there to un vector, then you can say that the first element of this basis, you can say the second element of the basis.
Yeah.
But when that's a set, you cannot talk about the first element, the second element. You cannot say. But when you write it as a sequence, you can say that that's the first element, that's the second element, that's the nth element. That's the difference. The ordering has been,
So, yeah, I think I can explain it like so. When you consider the natural number, the one comes first, right? Then 2, then 3, then 4, and so on. Then let's consider n. So, and I can write 1 as u1 vector, then u2 vector, then u3 vector, and u4 vector.
But as far as the notations are concerned, they can ask the same question that when you write it as a set,
Yeah.
they are also in bijection. Well, why aren't they ordered?
Yeah. So just for the set, yeah, because when I'm considering the sequence, that is not actually a set, right?
Yeah, but when you are writing the set,
notation
you also have,
Yeah.
you also have u1 vector that is associated with 1, u2 vector is associated with 2,
Yeah.
un vector is associated with
Then
n.
the argument
The order
fails.
does not matter.
Yeah.
Then the argument fails actually. Yeah.
So that's the thing that
Yeah. So
we cannot accept like that.
no.
Yeah, when you say a sequence, ordering is imposed by bijection.
Yeah.
That is right, but somehow when we are writing set, this is
Actually, sir, it is something like when we are considering sequence, the order actually matters, and we are not saying that sequence is a set, right?
Like the sequence should not be set.
yeah. But when we are writing set, we also associate these entries with the set of natural numbers, but
Yeah.
where the order don't matter.
Yeah, because even if we take like 1, 2, 3, in there is no order in the set.
There is no order, right? You're right, but when we are writing u1 vector,
Yeah.
u2 vector, all the way up to un vector,
Yeah.
u1 is associated with 1,
Yeah.
u2 is associated with 2, un is associated with n.
Yeah. Right.
But still order does not matter in this case.
Yeah. When I'm considering this to be a set.
Yeah, but you have the bijection.
Yeah.
But you were saying that whenever you have a bijection, there is an ordering. Is it what you were saying?
No, sir. I'm just looking the sequence in terms of the a map. So what I'm writing this, just consider this to be a UN sequence.
Yeah, that's fine. But in the set, you also have this bijection.
Yeah.
That is not an ordered set.
Yeah.
But why are you comparing an ordered set with this bijection? Did you get my question?
Yeah. I understand that.
Anyway, that's not very important. Let's carry on.
Yeah. Okay.
It's an ordered basis.
Right. When I'm writing this is like this is an ordered basis. But
That's right.
since it is a basis, then I can construct this set, and this set is linearly independent, and
It's just a basis.
yeah, it's the basis of this vector space field, right? So So the ordered basis is the set together with the specific ordering. Okay. So that is the definition. We are setting this as a definition that ordered basis is a set which has a particular ordering in that set. And yeah.
Yeah. What temperature is this?
It's 18.
Let's just increase it to 24.
Yeah. It's crazy.
Okay. So we can. So we have to do a abuse of notation here.
Yeah.
And
There is always that information.
okay, so I'm considering this to be a ordered basis. The U1 vector,
Yeah.
U2 vector.
It is also written as a set.
Yeah. But here ordered matters.
Ordered set.
Yeah. So for any vector in this vector space V, I can write it in terms of this basis, right? So if I consider this vector U belongs to V, so there exist unique n tuple x1, x2, xn belongs to of scalars, where if xi belongs to this this field F, then I can write this vector U in terms of this basis, and that will be I equals to 1 to n xi ui vector. Okay. Since it is a basis, I can definitely write a vector in terms of this, in terms of a linear combination of all these basis elements, right? So that, so if, so why I am saying this to be all these intervals are unique?
Because
Why these are unique?
I think because of the diagram definition.
No, just
Oh,
it is.
for the vector space to span the entire, for the basis to span the entire vector space between to be,
Yeah.
like we proved in the last class that
Yeah.
potentially.
So if you just consider if there exists, if this is not unique, then what you can write? So then there exists another n tuple y1, y2 dot dot yn, right? So if this is also exist, then I can write this u vector as in terms of I equals to 1 to n yi ui vector, right? And if you just if you subtract these two vectors, then you are getting 0 is equals to I equals to 1 to n xi minus yi ui vector. But we know that the set u, this is a basis, so it is linearly independent, and since it is linearly independent, that means all these xi minus yi is equals to 0. That means xi equals to y. So that means these scalars in tuples, these are unique, right? Okay. Yeah.
Can you explain the difference between non-ordering and unordering and ordering? I'm just not getting it.
Yeah. Okay. So for the ordered set, you can always compare two elements.
Yeah.
But-
For field, we have defined that order
Yeah.
field. We have defined
So that's why,
we have an order relation.
yeah,
Like that.
and that order relation is what? For two elements in that set,
Yeah.
if you consider the field x comma y belongs to f, then there is three consequence of this two elements. For either x is greater y, or x equal to y, or x is less than y. But if this field has no ordering, then there exists some element for a unordered set. You cannot define a relation like this. Okay.
Then for the linear independent set, linear independent vectors, how can we define an order?
Yeah, I
Like
just
we can use this relation here.
yeah. Just let me get this straight. So for a unordered set, you can just compare like subsets,
Yeah.
right? Because for the subset relation, there is like, just consider this 1, 2, 3, and if you take all the subsets of this set, you are getting 5, 1, 2, 3, 1, 2, 2, 3, 1, 3, and 1, 2, 3. So you see, now if I choose the relation as a subset relation, then you cannot compare 1 with 2.
What is subset?
Yeah, so I mean the inclusion relation, if you take the inclusion relation.
What is that?
Okay, so inclusion relation is something like just this is the inclusion.
Oh.
Okay. So now if you try to compare all these elements, can you do that?
No.
No, you cannot, right? Because you cannot compare 1 with 2, but you can compare 1 with 1, 2, and 1, 2, 3. So these three sets, if you consider these three sets, 1, 1, 2, and 1, 2, 3, then this is what? This is the ordered set.
Yeah.
And what is the relation here?
Illusion.
Inclusion relation. Because why this is the ordered set? Because 1 is a subset, sorry, just 1, 2 is 1, 2, 3. So you see, this is the ordered set, but this is not. This is actually a partially ordered set. Okay? Why this is a partially ordered set?
Because if it is subsets of them, there is an order.
Yeah. But if you just consider this set, there is no order here. You see?
There is no order.
Yeah. Because there is no relation you can relate one component to one of these elements to another. So for a ordering, you must need a relation.
For ordering.
Yeah. So that means, so now if you consider the field, so why there is a ordering in the field? Because you have a relation, and that relation is greater than, less than, or equal to. So that's why, and you can compare all the elements with each other. Either it is greater than one another one, it can be less than another one, or it can be equal to that number, right? So that's why there is a relation, and that's why this is
Ordering.
ordering. There exists an order.
For vector sequence, what are we